Okay, yeah, so welcome to those who are here. Welcome to anybody who's listening on a recording to the live stream discussion of the term 3 from last year, Math1231 exam with the algebra questions with David Angel and Daniel Mansfield. So I'll start with this one. This is question 1, part 5. Question 1 was half calculus, and then the algebra starts here. And here's the question, just a quick look through first. You're given a set W, it's a set of polynomials in P2, defined by this sort of equation. I've slightly changed some of the questions to word them a bit better. So this is expression for some alpha beta in R. We have to show that W contains the zero polynomial. Does this polynomial belong to W? Give reasons. And then something to do with writing W as the span of polynomials, find a basis dimension. Okay, so let's have a look at a few of these. So let's start right now in a solution for part A. And if you haven't been to any lectures lately, you may not be used to this, but I will be asking you to do questions, and please to try and tell me some answers in chat. That's the best way to learn things, is to think about it for yourselves. That involves answering questions. So we want to show that W contains the zero polynomial. Well, I hope you remember from lectures, what I really suggest to do with this in things like subspace proofs, etc., is to start off by stating quite clearly what the zero vector or zero polynomial is. So we'll say the zero polynomial, and we're talking about P2, if you look back at the question, is P of X equals. So just to say a bit more about that, I'm going to sort of keep some proper solutions here and also a bit of a scratch pad. So for example, say we're in M22, I'd say if I want to show that a certain set contains the zero matrix, I would say the zero matrix. Yep. And what is it? If we're talking about M22, it's this here. And if it was a subspace question, I would then say that is in S, and then I would give some reasons. Okay. And similarly, if it was, let's say, R5, I would say the zero vector. And then I would say specifically what it is in the set S again, and then give reasons. Okay, so going back here, could anybody please type a formula for the zero polynomial in P2? What should I write down for P of X? Any suggestions? Say something in the microphone, please, or type in chat. What's a formula for the zero polynomial? Okay, thanks, Dominic. Yeah, that's exactly it. It means that all the coefficients are zero. In other words, 0 plus 0x plus 0x squared. Okay, and we want to know if that's in W or not. Well, it's in W if it's equal to the formula given, which I'll just copy down. You've got it in the question. It was alpha plus 3 beta plus alpha minus beta x plus 2 alpha minus beta x squared. And if we can show it is equal to that for certain values of alpha and beta, then we're done. That is in the set S. So, and I think that's very easy. I don't think you need to really solve anything. Just look at it. Can anybody provide values for alpha and beta? There's lots actually, but there's one pair of values which is much easier than all the others. Suggestions, please. Just 0, 0. Yep, great, thanks. So for alpha equals 0, beta equals 0. Okay, that's obvious, right? You don't need to solve anything. Just look at it. If alpha and beta are both 0, then you can see that's 0 plus 0x plus 0x squared. In other words, it is that polynomial. Okay, so since that is equal to this formula, that means so the zero polynomial is in W. Okay, and just one thing I'd like to comment on there, which is that I think the actual mathematics, the algebra that you have to do there is very, very easy. Just look at that and say, if we take alpha and beta 0, then this is the zero polynomial. But writing it up carefully is also important. So any questions on that part? Okay, let's go on to part B. And I can do that quite similarly, actually. So the polynomial 1 plus x plus 2x squared. Well, let's just look at this. We want to know if that is equal to this formula here for certain values of alpha and beta. And normally we'd probably want to solve some equations, but if you look carefully, you might be able to find values of alpha and beta. Anybody want to give it a try? Can you just look at this carefully and find values of alpha and beta, which will make this equal to 1 plus x plus 2x squared? Just have a careful look. A equals 1, or alpha equals 1, beta equals 0. Great. Can we see that? And you can see that, I think, just by looking at it. If alpha is 1, beta is 0, then that's 1 plus 1 times x plus 2 times x squared. We've got that. Okay, so that is equal to this same polynomial. When alpha equals 1, beta equals 0. And so it's in W. So it's in W, or it belongs to W. Okay. Let me just try something else with that. Now, you can do that if you look carefully. Suppose we asked you a similar question, but more revolting numbers, like say this was, say, I don't know, 57 alpha plus 32 beta plus alpha minus 99 beta plus 203 alpha minus 4 beta. And I asked you, what about 5 minus a million x plus 200 x squared? Then obviously you wouldn't expect to just look at this and get an answer. So how would you do it in that case? Well, so in that case, you would want to do something like this. You'd want to say alpha plus 3 beta. Well, if this polynomial equals that one, then, or this one equals that one, then alpha plus 3 beta equals 1. I don't need the brackets there, I'll get rid of them. And then also alpha minus beta must be the coefficient of x, which is 1. And then 2 alpha minus beta must equal 2, coefficient of x squared. Okay, and then you could solve that. You know how to solve that by putting the system into matrix form and row reducing, and you'd either find a solution which proves that the polynomial is in W, or you'd find that there's no solution which proves the polynomial is not in W. However, in general, if you can see a shortcut with calculations, just go for it. That's absolutely fine. No problems with that at all. On the other hand, I would say when it comes to give reasons, don't take shortcuts there. You need to have full, clear explanations in all your reasons. But for calculations, if you can see a shortcut, go for it. So any questions on part B? Okay, I can see we've got a few more people arrived just recently. So let me just say what I said at the beginning. If you have any questions, please don't hesitate to ask. Say something into a microphone or put a question in chat. That's very welcome. Okay, so if there's no more questions, let's go on to part C. And that was the following. And I've put them as 3 separate parts, but I've combined them into one question. Write W as the span of a set of polynomials. I think it originally asked, is W the span of a set of polynomials? But I think this is a better question, so I've just slightly changed it. Find a basis for W with brief reasons. State the dimension of W. Okay, so we've got to write W as a span of a set of polynomials. Let's firstly just copy down what W is. So it's the set of all, and I can write this in a slightly different way. I don't have to say P here. I can just put this expression before the colon and alpha beta in R afterwards. So it's alpha plus 3 beta plus alpha minus beta times x plus 2 alpha minus beta x squared, such that alpha and beta are in R. Okay. If you've been following my lecture notes carefully, you might notice I usually put a vertical line there instead of a colon, but it doesn't matter. Both notations are fine. Now, we want to write that as the span of a set of polynomials. Now, again, something which I've mentioned quite frequently in lectures. I hope people have picked up on this. First important thing is to make sure you know what the words mean. Okay, so can I ask people to write down, just for yourselves, write down what's meant by, let's say, the span of, let's say we've got a set containing 3 vectors. Let's make them polynomials, as in this example. So could I ask everybody, please, just for yourselves, just write down somewhere, what does that actually mean? I'll give you 15, 20 seconds to think about it and do some writing. Okay, so I hope you've written something like this. It's the set of all linear combinations of these. So it's the set of all expressions lambda1 p1 plus lambda2 p2 plus lambda3 p3, such that lambda1, lambda2, lambda3 are any scalars, and in this case, let's say they're real numbers. That's what we want for this question. So in other words, what it comes down to is, to show that this is the span of some polynomials, I have to write it as a scalar times a polynomial, plus a scalar times another polynomial, etc., and as many terms as you need. And notice here, what we're thinking of is that the polynomials will be specific fixed polynomials, like 1 or 1 plus 2x or x squared or something, whereas the constants, the lambda1, lambda2, lambda3, they can be variables. And so we've done this kind of thing a couple of times in lectures. So let me just start it off for you. The easiest way, there are lots of ways to do it, in fact, but the easiest way is just to look at that alpha there. And so I've got alpha times, what have I got alpha times in this expression? Well, here I've got alpha, just alpha, which is alpha times 1. And here I've got alpha times x, so that's alpha times x. And here I've got 2 alpha x squared, so that's alpha times 2x squared. Okay? Now that, at this stage, obviously is not the same as that. So we'll do something with beta. And could anybody type in or say, what will I have beta times what? Can anybody just tell us a polynomial? Just look carefully at this. We've got beta times 3 minus x. Yeah. Can everybody see that? So we've got 3 beta, which is beta times 3. We've got minus beta x, which is plus beta times minus x. And we've got minus beta x squared, which is plus beta times minus x squared. And alpha beta are still real numbers. Okay. And that's pretty much answered the question, because you see what we got here? This here is a linear combination of those two polynomials, except it's not just a linear combination, it's every possible linear combination, because alpha and beta can be anything, and therefore, by definition, it is the span of those two polynomials. And that's the answer. Any questions on this one? Okay. What I might suggest is, if we've got time left at the end of the session, people can come back and ask similar questions. So, for example, if you wanted to see an example of this kind of question, but let's say in M22 or R3 or something, then we could do an example like that. But let's just do the questions we've got at this stage. Next question is find a basis for W. And once again, before anything else, the most important thing is to know what the words mean. So can everybody please just write down for yourselves what exactly is meant by a basis for a vector space? And I'll give you perhaps 10 seconds to do that one. Okay, so I hope you've written down that a basis for a vector space is a set which is a spanning set for the space and also is linearly independent. Now, if you think about it, a spanning set for the space is really obvious. If I say the span of this set equals W, that's the same thing as saying this is a spanning set for W. Okay, now if it's a spanning set, the ideal thing, the easiest possible thing would be hopefully it's independent as well, in which case it's a basis. If not, we have a theorem which says we can remove some of these polynomials to form a basis. So let's go for the easy one first. Can anybody tell if these polynomials are independent? And I hope you recall there's lots of ways of telling independence, but there's one spectacularly easy shortcut which sometimes works. Any ideas? Why are these independent, and can you give a reason why? So just a yes or no first and a reason. Well, I'll give you a hint. They are in fact independent. And what's the easy shortcut for showing that two vectors are independent? Yeah, coefficients not multiplied. Yeah, great. So we've got two vectors, thanks Mohammed. They are two vectors and they are not multiples of each other, therefore they are independent. So basis for W is, here's our answer, it's just that set there. Okay, and reasons. I say, first of all, the above, let's give it a name to save a bit of writing. I'll call it B. B equals that set there. The above shows that B is a spanning set. for W. And secondly, the two polynomials in B are independent because they are not scalar multiples of each other. And as for that last statement, I hope that's obvious enough just by looking at it. Suppose they were, then looking at the constants, this polynomial would have to be 3 times this one, but that works for the constant. It doesn't work for the x or x squared terms, so they're not scalar multiples of each other. Okay, so any questions on that bit? Okay, and finally, state the dimension of W. So anybody like to type up a number or say a number? 2, yeah, basically, thanks, Gabriel. Yeah, so basically all you have to do is, have to know what dimension means. It means the number of vectors in a basis. In this case, it's the number of polynomials in a basis, and we've got a basis and it's got 2. Okay, two polynomials in it. Let's just give a brief reason. So because B contains 2 polynomials. Okay, although if the question says state, we usually understand that to mean reasons are not required. Nevertheless, it doesn't hurt to put reasons if appropriate. Before I hand over to Daniel, I'd like to do one more thing, which is just to mention, because this is something people sometimes get wrong, this reason we have for independence. They're not scalar multiples of each other, and it works because there are 2 polynomials. Remember, that does not work for more than 2 polynomials. Let's go back to my scratch pad here. If I have 1 plus x plus 2x squared and 3 minus x squared, okay? And let's take a polynomial, let's say just 4 plus x squared, which I've obtained from those 2 in a way which I think is probably pretty obvious. Now, those polynomials are going to be linearly dependent. Why is that? Because linearly dependent means I can do scalar times this plus scalar times this plus scalar times this equals 0, where the scalars are not all 0. And I can do that because I can just take 1. This is how I wrote it down so easily. I just added those 2 things, in fact. Okay, so therefore they are linearly dependent. However, if you look at pairs, you could say those 2 are not scalar multiples. Those 2 are not scalar multiples. Those 2 are not scalar multiples. And therefore you might be tricked into thinking they are independent because no 2 of those polynomials are multiples of each other. But that's not correct, because remember, that method only works if you have 2 polynomials or 2 matrices or 2 vectors. So any more questions on any of these things? Okay, Daniel, over to you.
Okay, so thank you, David. I'm glad you mentioned that this thing with having 2 vectors independent does not generalize to 3 vectors, because I do see that cropping up a lot, and you might build some intuition about multiples, which does not extend.
Yeah, I agree. Yeah, thanks.
Awesome. Now I'm going to attempt to share my screen. Now, David, just a word of warning. Sometimes when I do this, my computer freezes up. So if it does freeze up, you'll just have to stall them for a moment while I restart everything. So here we go. Oh, no, it worked just fine. Hey, hello, everybody. So the next algebra question on our list is this one. So just put that over there. Let us read the question together first. Part A asks us to manipulate the power series, this one here, or otherwise, and to show that this thing occurs. Okay, that's pretty standard. And then this one here about a geometric distribution initially might appear unrelated, but let's just trust that the question has been sensibly constructed. And then some kind of application of this geometric series here. So we're given something about Taylor's or power series, and then something about distributions, and something that probably relates to part B. Let's have a crack at this, shall we? So part A. Given 1 minus x is the sum from k equals 0 to infinity of x to the k for minus 1 less than x less than 1. Now, the good news is that these power series are very robust objects. You can add them, you can multiply them, you can integrate them, and you can differentiate them. And where I'm trying to get is from this object, this sum of the xk's, to this object, where the power here has been decremented, and I've got a k out front. Would anyone like to suggest how I might get from a beast looking like this to a beast looking like this? What operation could we use to mold this object into this object? I can hear something going on in chat. Yes, Teresa, differentiate. That is how we'll get there. And this is great. This is a great suggestion for you in a ratio test. We're not actually asked to show that that this converges. We're given this. This is our tool. No, that's totally fine. It's an interesting question if it does converge, and you could totally use the ratio test to do that. But we're just told to take it for granted. You don't need to do anything fancy. So we're just given this, and I'll differentiate by x. Well, on one hand, this gives us dx of 1 on 1 minus x, which is equal to, so that's the left-hand side. That's going to be, I'm going to have to do this, 1 minus x, multiplied by that, the derivative of that thing, and then times 1 minus 1, and the minuses all cancel, and I get 1 on, there's a square there now, 1 minus x all squared. And the right-hand side is equal to dx of this sum. Hello, hey Josh. Sorry, I haven't. K equals 0 to infinity of x to the k, which is equal to the sum from k equals 0 to infinity of the derivative of each of those terms. So that's just going to be kx to the k minus 1, hence, and maybe I'll just clarify 4 minus 1 less than x less than 1. So you can't pull this kind of stunt for x values anywhere. You can only pull them for x values in that range where this power series is defined. Hence, well, the left-hand side, which is 1 on 1 minus x all squared, is the derivative of the left-hand side is equal to the derivative of the right-hand side. The sum from k equals 0 to infinity of k times x to the, oh, not to the one that's going to start from 1 now, because that constant term, that initial constant term that was up here, when that got differentiated, that died. So that starts from 1, or didn't die, just went to 0. That thing, which is what we were required to show. Oh, it actually says k equals 1. So in the question it says k equals 1, which I guess is the same thing, because I can just start this series from k equals 1. Because that initial term when k equals 0 is just 0 anyway. Alrighty, that was part A. Oh, sorry, I'm just going to check this chat. I can see Josh and Josh is telling me stuff. Okay, cool.
No worries, Daniel. It's all okay.
I'm getting back to, all right, cool. Sounded like something I might have needed to look at. Anyway, part B. Let's have a look at part B. Seemingly unrelated question. If X is a random variable with geometric distribution that, GP, which is to say, and this is very nice of them to actually tell you exactly what it means, show that the expected value of X is this thing. Okay. Let's go on to part B. So suppose X, now this is a notation G of P. That is to say, X is a random variable and it has this distribution, so the probability that capital X is equal to any particular value is just P times 1 minus P to the K minus 1, where P is P has to be a positive integer. So X can be equal to 1, 2, 3, 4, stuff like that. I like to have a drawing with all my questions, so I'm just going to draw something real quick. The geometric distribution might be a little strange because it's really the other distribution, the poor cousin to the one we study in great detail, which is the binomial distribution. So this one doesn't come up nearly as much. So let's just have a look at some values here. So this is my kind of little k axis, and all the different values that this thing can take, like 1, 2, 3, and so on. And if you like, this distribution can be imagined as this kind of like a bar chart. You've got all these bars. Maybe I'll make that one a bit thicker. This one here is of height P. Think about it as like an area. This one here is height P. This one here is height slightly less than that. It's P times 1 minus P. This one here will be a fraction less, P times 1 minus P squared, and so on, all the way out. So dot, 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 all the way up to infinity. Okay, now this tells me about all the probabilities, and it tells me it in a nice visual way, which I think is very pleasant. It asks for the expected value of X. Now, the expected value of X might be a little bit strange. Let's talk about the expected X. Expected value of X is a bit like the average, but it's not the average in the sense where you take all the possible values of X and divide by the number of values. It's the average in the sense of weighted average. You take all the possible values that X can take, which is K equals 1 to infinity, and you take those values, and then you don't take their average, you take the probability with which that value could occur. So that would be the probability that X is equal to K. You see, these random variables aren't like variables that you know and love. Not like find X, where X is part of a quadratic equation. No. When you've got a random variable, the most you can know about it is this distribution of values that it can possibly take, and how likely each of the possible outcomes are. So here we have the expected value of X. It's always going to be this. Doesn't matter what your random variable is. It'll always have this form of the values of X multiplied by all the probabilities of X being that value. And thankfully, we know exactly what each of those probabilities are by their formula, which was given to us. So this is the sum from K equals 1 to infinity of K times by p times by 1 minus p to the k minus 1. Ah, and maybe at this point, maybe it's at this point that you realize that you've been, the person who wrote this question was really a very kind person who guided your hand the whole way and gave you this form, this stuff here to help you down here. This isn't a random jumble of questions. This stuff is going to help you here. I might take a little bit, I might make things a little bit more obvious for you. I'll take out that p, which is just a constant, and I'm going to write this as k equals 1 to infinity of k times x to the k minus 1, where 1 minus p is equal to x, is something. Let's be real careful here, because we're about to invoke part A, but part A, I'll remind you, is only valid for this x's in this range. Let's just consider what could possibly be going on here. If p is equal to 0, then that's not good. We can't have p equal to 0. I mean, the wheels fall off if p is equal to 0 anyway. You've got all sorts of trouble. So maybe we'll assert for p. P is in the range 0 to 1. 1's okay. So this thing is going to be somewhere between 1 and, well, if p is equal to 1, then this thing's equal to 0. So we're definitely in that range, -1 to 1, the required range there. Now this thing is just equal to p times, well, by what we were given previously, that's going to be 1 over 1 minus x all squared, which is equal to p over times 1 over, remember x is just 1 minus p, so that's 1 minus p squared, which is just going to be p squared, which is 1 over p, which is the thing we were required to prove. Are there any questions about that? If there are, please just pop them into chat.
Just a question for students to think about. What would actually be happening if p is 0? Remember what sort of situation the geometric distribution models. Could anybody suggest any answers to that? What's the typical sort of situation? We can things in lectures about tossing coins and so on. Okay, well, if you remember, what happens is that for the geometric distribution, it's for waiting time problems. Okay, so like you're tossing a coin, and you want to know what's the probability that you get a head for the first time. In fact, I think this is what's coming up in part C of the question. You get a head for the first time on the 10th toss, for example, and that's where the probability of getting a head on any toss is p. Now, what's going to happen if the probability of getting a head happens to be 0? And you're going to try and count how many tosses it takes you to get the first head? Well, it's never going to happen, is it? So speaking roughly, you could say it's definitely going to take you an infinite number of tosses. Not really good to say that precisely, because infinity is not a number like other numbers. But roughly speaking, it's going to take you an infinite number of tosses. And so you could say this is kind of, again, just very roughly speaking, this answer is kind of right, 1 over 0, infinity, sort of. Okay, don't say that literally, always put it in quotes, but it's something like right.
Yeah, and conversely, if you have p equals 1, then you get your positive outcome on the first toss, which is totally fine.
Yeah, all of this stuff that Daniel and I are saying just at the moment, you don't need it to answer the question, but it's good to be thinking about these kind of things.
Yeah. Part C. By the way, David, did you write this question?
No, I didn't.
The person
No.
who wrote it was very lovely. I think this person has really thought about what question guiding, I think, the people through this process by providing part A, part B, and even part C. The person, yeah, I think this was a very nicely crafted question. So part C. Part C. Paul tosses a biased coin. The probability that he tosses a head is only 0.2. Find the expected number of tails tossed before Paul tosses the first head. And this is exactly what David was just mentioning about waiting time. So really the geometric distribution is modeling the waiting time. It's the number of tosses of the coin until that you have to do until that first success. So here you have the probability that x is k, being the probability of having k minus 1 initial failures followed by success on the kth toss. So this is really, and anytime you find yourself in that situation where you're looking for failure, 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 and then success, that's really the scenario where you start using or should be thinking about the geometric distribution. So that's exactly what we're given here. We're given the probability of success is 0.2, and the probability, well, it's really just asking us what is the expected value of x. So for part C, suppose x equals number of coin until so this is, x is the random variable, which is the number of coin tosses until the first head appears. Then our random variable x has the geometric distribution. The probability of success is 1/5 or 0.2. So expected value of x is equal to is just going to be equal to 1/5 by equals, which is just equal to 5 by part A. It might be a little bit safe here. The question actually asks us for the expected number of tails tossed. So this is the number of tosses. And so we might say the expected, so by part A, so there so we expect, I'll write it a bit differently. So we expect first by the, well, you can't see what I'm writing, the fifth toss, which is to say 4 tails. Just to be really clear that I am actually answering the question. Geometric distribution tells you about stopping times, which is very, very closely related to the number of failed times. Literally x saying your number of coin tosses until success, which is going to be 1 more than the number of fails you have to get before a success. Alrighty. I think that's all I want to say about this question. Are there any to that, David, or anything you'd like to comment on?
No, I think that's fine. I just think just that end of the question there just illustrates the importance of reading the question carefully, because it would just be very easy to write down e of x equals 5, go to next question. But make sure you read carefully. Yeah.
Can we do 1/5 of? Can we do? Let me think about that, David. Do you want to get onto the question? I'll have a think about Wei-Lin's question. Can we?
Okay. Yeah, so that would be saying that the probability is less than 1, and unless it happens to be equal to 1, that must always be true. So I think that's would be answering a completely different question. Okay, because the question is about the expected number of tails, so you have to using e of x somehow.
Yeah, and well, that's always going to be less than 1, your P, so P of X equals K is less than 1 for all K. That's always true. And the question's asking you about the expected number. So I'd really be inclined to go on. Sorry, David.
So I was just going to say, I think, Waylon, perhaps you're thinking of some other questions which occasionally get asked, like find a value of K such that the probability X is less than K is a half or something like that. Maybe you're thinking of that kind of question, but this one's quite different. Yeah, I'm not quite sure. Yeah, okay.
Yeah. Great. We will be doing a question like that. No problem. Thank you for asking a question. Makes me feel like it makes me feel good about myself when people do that. David, over to you.
Okay, so let's go on. I'll share my screen back again. I'll try and remember to do that this time. So here we go. Okay, so here's the next question. We're now starting off question 2 with a bit more algebra, and let's just read through this a bit slowly because there's a lot of information to get here. So let V be a vector space. The dimension is 3, and I guess as soon as you see that, you should be just, even if you know it really well, just quickly think mentally, what does that mean? It means there's a basis for V which has 3 vectors in it. Let T from V to V be a linear map. Okay, and I hope you recall what's meant by a linear map. In fact, I'll ask you, can people write that down for yourselves straight away? What if I say T from V to V is a linear map? That means 2 conditions. Could everybody please try writing them down? And if you feel like it, type them in chat as well. Because once again, always really important to make sure you know what the terminology means. Otherwise, you're getting nowhere. Okay, so I hope people have had the chance to write all that down. It means that T of U plus V is always equal to T of U plus T of V, and T of lambda times V is always equal to lambda times T of V. So that's T from V to V is a linear map. Suppose that both this set and that set, they're both linearly independent. Subsets of V, notice T is from V to V. So that means when you write down something like T of V, the V values are in capital V, and the T of V values are also in capital V. So therefore, they're both subsets of V, and we're saying they're linearly independent. Suppose you're given this completely irrelevant-looking equation. Well, we'll see if we can do something with it later. So first question, find a non-zero vector V in, and I'll just point out there was actually a typo in the exam. It said the kernel of V, which makes no sense. It should be the kernel of T. So find a non-zero vector in that and give reasons. Secondly, find the rank and the nullity and give reasons. Okay, so once again, and I hope I'm not being boring saying this, but once again, you have to know what things mean. So could anybody please provide an answer? What does it mean to say that V is in the kernel of T? Could anybody type an answer or say an answer to that? Yeah, T of V equals 0. Right. Hope everyone knows that, right? Because that's very important to know what it means. If you don't know what it means, you might as well just go to the next question. Okay, so that's what it means. So we have to find T of something equals 0. And can I also mention, I meant to say this at the beginning, this is, I think it's pretty clear that this is not just your standard question, given some specific vectors, find dimensions, find ranks, etc. Like the previous question I did was much like that. Here, it's obviously a much more theoretical one. And so if I just, for example, if I just go straight through and write down an answer to this, I really don't think it's going to teach anybody anything. What I would like to try and teach you is how to think about questions like this. Okay, because if we get one, which is also a theoretical one in the coming exam, but it's not the same as this, then the actual answer to this is not going to help you at all, but the methods that you can think about hopefully will help you. So, okay, we've got to we're asked to find a non-zero vector V, which is in the kernel of T. In other words, T of something equals 0. Okay. Any ideas where we could start? Just looking through the question, anything that could possibly be relevant? If you want to refer to it, just say that's line 1 in the question, line 2, line 3, line 4, just to make it a bit easier. Anything that could possibly be relevant? Here's an important thing to think about for a start. If you can think of anything which might work, try it. If you don't know for sure it's going to work, try it. You have to be prepared to do something that's not going to work and cross it out and start again. Can anybody see anything that might possibly be relevant to finding t of something equals 0? Line 5, the equation. Yeah, I think so. And Gabriel, I don't know if this is what you're thinking about. This is the way I would think about it. We've got to show t of v. Let's just concentrate on that. Equals. There is only one equals in the whole of this question. Oh, I guess there's another one, isn't there? Okay, never mind that one. Okay, but there's basically only one equals in the whole of this question. So that looks like this line 5 has got to be relevant somehow. Let's just copy it down before we do anything else. So I'll copy that down. So t of v3, and I'm going to just do treat this as a scratch pad. And once we've worked out what the important thing is, then we'll write down the answer properly. Okay, now this equation is obviously not the same as that equation. And there's a number of very obvious differences between them. But let me perhaps give you a hint, just for a start, that this one has 0 on the right-hand side. Does that give anybody any ideas as to something you could do perhaps for a start with this equation? Please type or say something if you have any ideas. And like I said before, if you're not sure it's going to work, doesn't matter. You've got to try it. Teresa, I'm not totally sure what you mean by equate to 0. Okay, I guess so, but then V1 and V2 are going to be specific vectors. We don't get to choose them. Yeah, I think, Mohammed, I think that's a much better idea. If we move everything to the left-hand side, then the right-hand side is going to be 0. But thanks to other people for the suggestions anyway, because like I said, you must not just say, I'm not sure it's going to work, I won't try it. If you're not sure it's going to work, you've got to try it. Okay? And if it doesn't work, big deal, cross it out, start again. It does not matter. We've got plenty of paper to give you, not that you'll be using paper, I think, for this exam this term, but you know what I mean. Okay, so I think, Mohammed, that's a much better idea because we can get an equation with 0 on the right-hand side by moving everything to the left-hand side. Let's do it. So that's t of v1 minus 3t of v2 plus t of v3 equals 0. Okay, now this looks much better already because we've got this, okay, that they correspond. Don't worry about the scribbles. Like I said, this is a scratch pad. I'm going to write a proper answer once we've got the idea. Now, the other thing you might notice is that now, think of this as being our target. That's what we want to get. That's our aim. And the biggest difference you might notice here is that there's only one term on the left-hand side. In this case, there's 3 terms on the left-hand side. Any ideas for how to deal with that? So our aim is to have t of something equals 0. Remember what a linear transformation means. We revised what that means just a couple of minutes ago. So t is linear. Thanks, Waylin. That's a good point. How can we use it? Can we use the fact that t is linear to put something in the blank here? That's exactly what we need to do, that t is linear. So v1, yeah. So can everybody see what you get here? Because t is linear, that means I can put the constants inside the brackets. We often think of it actually the other way around. Take the constant outside the brackets. T of lambda v equals lambda t of v. But of course, that's an equation. If left-hand side equals right-hand side, we can say right-hand side equals left-hand side. Doesn't matter. Okay, so I can say minus 3 t of v2 is t of minus 3 v2. And the other thing about a linear transformation is that you can combine sums. So this left-hand side here is going to be v1 minus 3 v2 plus v3. Okay, that's just another way of writing it. And now we've got our aim. We've got t of something equals 0. So I'm going to say v equals v1 minus 3 v2 plus v3. Okay, and so find a vector v in the kernel. I've done that. Can everybody have a careful look at question A? And can you say, have we finished yet? Is there anything else we need to do about this v? I've proved it's in the kernel of t because t of v equals 0. Anything else I have to prove? Read the question carefully. Show it's, thanks both Teresa and Dominic. Yeah, show it's not 0. It says clearly a non-zero vector. Is it obvious that v is not 0? it's not at all obvious, therefore we have to think about it. So how can we show that that's not 0? Well, again, can anybody have any ideas about this? Look at the information that's given in the question. Can anybody see any relevant information? And again, if you like, refer to a line number. The vectors are independent, yeah, so lots of people got that, great. What does it mean that they're independent? That means that for this to be 0, let's write v equals 0 question mark. Since they're independent, that means that the coefficients are 0, all of them. But that's obviously not true because the coefficients are 1, minus 3, 1. So that's not true, and therefore v can't be equal to 0. Okay, now has everybody got the idea of this? Any questions about the ideas? Okay, so like I said, now we need to write it up carefully. We have to find a non-zero vector v in the kernel of T. If you've done the working, we may as well start off with the answer. So here's our answer to part A. So I'm not going to go through and find it like this. That's my scratch pad, that's my rough working. But for the actual answer, I may as well just say, this is what I want v to be. So I'll say let v equal, what was it, v1 minus 3v2 plus v3. Okay, then I can say, what's t of v? I want, first of all, I'll prove that it's in the kernel. So t of v is t of v1 minus 3v2 plus v3, and that's t of v1 minus 3 t of v2 plus t of v3. And I'll put a bit of an explanation in the margin, since t is linear. Okay, but let's say, but we know, let's write down the equation that was given, that's this one here, that t of v3 equals 3t of v2 minus t of v1. And if you substitute that in, you've got t of v1 minus 3t of v2 plus 3t of v2 minus t of v1. So that equals 0. And hence, that means that v is in the kernel of T. Okay, also, we know that v1, v2, v3 are linearly independent. So if v equals 0, then, well, let's put it this way. If they're linearly independent, we have to consider, so I'll just pop that up there. I have to consider lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 equals 0 has the unique solution lambda 1 equals 0, lambda 2 equals 0, lambda 3 equals 0. But this is not the case because we know it has the solution what is it going to be? Where's v gone? Here's v. It's going to be lambda 1 equals 1, lambda 2 equals minus 3, lambda 3 equals 1. Okay, so this is impossible, so therefore v is not equal to 0. Okay. Any problems or questions about this bit? Okay, so please remember, like I'm saying, a more out-of-the-box question like this, don't expect to get exactly the same question in this year's exam, this term's exam. There could very well be something like that, but the important thing is not to memorize the solution, but to think about how could you approach it, what sort of questions can you ask yourselves. And then again, don't expect to just write down the answer. Something like this, you normally will have to have a good think about it, probably do a whole load of scribbling, and then come back and write down the answer properly. So any questions about that one? Okay, so let's start the next one. So we have to find the rank and the nullity of T. And once again, can I ask you please to spend 15-20 seconds writing down the definitions. What does rank of T mean? What does nullity of T mean? Okay, so perhaps I won't ask for answers this time, but I hope you've written down something like the following. Hang on, I'm just getting my pages in a muddle here. Okay, so I hope you've written down something like the following. So rank of T is the dimension of the image of T, and the nullity of T is the dimension of the kernel of T. Just a brief comment, sometimes people get things mixed up a bit with, say, between nullity and kernel. Remember that the kernel of T is a set of vectors. It's in fact a vector space. The nullity is just simply a number. And similarly for the image and rank, image is a set of vectors, it's a vector space. Rank is just a number. Okay, now let's use some Scratchpad material. So having a look at the information here, and again, can anybody say anything about the rank of T? So it's the dimension of the image of T. Remember, the image of T, again, perhaps I should have asked you to write down definition, but let me write that down. So the image of T, the kernel we've written down already basically, but the image of T is the same, remember, it's the same as the range in calculus. It's a set of all function values. In this case, the set of all T of V values, where V is in capital V. Now, can anybody see, well, in fact, if I put it this way, can anybody see any important things about T of V values in this question? Have a look at this. Image of T is V. Not quite true necessarily, because this means, this here, Gabriel, means that the image of T is a part of V. So image of T is a subset or a subspace of V, true. Image of T equals V, maybe not true. Maybe it is true, maybe it's not. What about that? Here are two elements that are definitely in the image. Remember, T of anything is in the image. Here are two elements in the image. And those two elements, we're told, are linearly independent. Now, what do we know about a vector space if it has two linearly independent elements in it? What do we know about the dimension of the vector space? Let me give you an example. Say, take R3. Is it possible to have R3 and have 4 linearly independent vectors? So rank equals to Lin-Yan, not quite, very nearly true. Could anybody fix up what Lin-Yan said? It's very nearly true, not quite. So for example, so let's forget about V particular. Let's take a specific example. Suppose can anybody answer? No? Can you find 2 linearly independent vectors in R3? Is that possible? No, yes, you can, certainly. Here you go. Here's 2 linearly independent vectors in R3. There's one, there's another, right? And in fact, I could give you a third one coming up out of the page like that. So here's 2 linearly independent vectors in R3. Does that mean the dimension of R3 is 2? No, certainly not, because you know what the dimension of R3 is, it's 3. So you can find 2 vectors, 2 independent vectors in R3. Let's turn it round and say something a bit different. If I tell you I've got let's say I've got 5 linearly independent vectors in Rn, what can you tell me about n? N is, yeah, so like when we go back to Lin-Yan's answer before, rank is equal to 2. Can anybody now say what's the correct answer about the rank? It's, yeah, so sorry, I should just say, actually just say we've got 2 contradictory answers. Gabriel was right. n is greater than or equal to 5, right? Not doesn't have to be equal to 5, right? Like here, we've got two linearly independent vectors in R3. That doesn't mean 3 equals 2. It's possible because 3 is greater than or equal to 2. So n is greater than or equal to 5. So we go back to when Linian said, in this situation, there's two linearly independent vectors, therefore the rank equals 2. Can anybody fix that statement, improve it? The rank is greater than or equal to 2, yeah. Not 2, maybe it's 2, maybe it's not, we don't know, but it must be greater than or equal to 2. Okay, so let's write that down. This is still our scribble page, so it doesn't matter which way we put it. So the rank of t is greater than or equal to 2, as there are two independent vectors in the image. Don't worry about all this scribble, it will be improved later. Okay, now let's ask something else. Anything you know about the nullity? It's the dimension of the kernel. And I'll give you a hint, think back to what we did in part A. Can we say anything about the nullity? We've got one non-zero vector. Dominique, I think not yet, but that is definitely going to be important later on, so I'm going to write it down. So the nullity plus the rank, so nullity of t plus rank of t is equal to the dimension of the domain, and that's the dimension of V, and we're told that that's 3. So that's definitely true, and I think we'll come back to that later. So here's what we know about the kernel. Sorry, let me find it. We know the kernel contains a non-zero vector. Think of it in R3 if you like. We know that the kernel contains a non-zero, maybe it contains others as well. We know it's a vector space, therefore it contains all scalar times that. So what can you say about the dimension of the kernel? So the kernel contains all of these vectors here. At least one, and good answer, at least one, because I didn't tell you anything else. Maybe the kernel contains other vectors as well, maybe. So we know the dimension is 1, at least. It could be more. So let's write that down. I've thrown my pages all over the place here, but where is it? Let's go back here. So I can say that the nullity of t is greater than or equal to 1, okay, as v is in the kernel and v is not equal to 0. Okay, now, can anybody just have a look at that? I think this might even be hard to explain because it's too obvious, but look at this. The rank is 2, maybe more. The nullity is 1, maybe more. They add up to 3. So what can we say exactly about the rank and nullity? Can everybody see? It's a bit hard to put into words in a way because it's kind of obvious. Because if this was bigger than 2 and this is 1, there's no way they add up to 3. If this was bigger than 1 and that's 2 or more, there's no way they add up to 3. If that's 2 or more, that's 1 or more, they add up to 3. There's no leeway, if you like to put it like that. This has to actually be equal to 2. This has to be actually equal to 1. Here's another way we could put it. I could say this, the nullity of t is going to be 3 minus the rank. Okay? And the rank of t, I should say rank of t all the time, not just rank. The rank of t is greater than or equal to 2, so that's less than or equal to, it's 3 minus 2 or more, so it's 1 or less. So the nullity of t is less than or equal to 1, but I also know it's greater than or equal to 1, therefore it's got to be 1. And therefore the rank is 2. Okay, and once again, can I just ask, like I said before, does everybody get the idea? If everybody's clear on the idea here, then we'll start writing it out carefully. Okay, let's go, let's try. So we'll say something like this. So part B, let's just read the question again and see where we start. So firstly it says find the rank. So let's approach the rank first. So we have rank of t, let's write down the definition first, is the dimension of the image of t. Also, the image of t contains two independent vectors. T of v1, t of v2. Okay, So I hope that's clear. They are in the image because the image contains t of anything, and they are independent because we were told so in the question. Okay, and so we'll get what comes out the rank. So the rank of t. Remember, that doesn't mean it's equal to 2. It's greater than or equal to 2. And perhaps I could put in a bit of explanation here. Contains 2 independent vectors and maybe more. Right? We were told that these two are independent. We were not told that it stops there. So image of t contains 2 independent vectors, t1, t of v1, t of v2, maybe more. Therefore, the rank of t is 2 or maybe more. Okay, so we got that. Let's come back to that later. So also, kernel of t contains a non-zero vector, specifically v from question A, and that means that the nullity of t, again, let's write in the definition, the dimension of the kernel of t must be at least 1, okay? And again, perhaps I won't write it down this time, but same reason as that. We know it contains 1 non-zero vector, therefore the dimension is 1, but it could contain more independent vectors as well, so the dimension could be more than 1. So we've got that. Also, we know the rank nullity theorem. Rank of t plus nullity of t equals dimension of v, which is 3. Also, let me just make a comment about exam questions. Exams, fortunately, are not real life. In real life, if you have to solve a problem, you may not have enough information. You might have to go and get more information. Or you might actually have more information that you need. Some of it turns out to be irrelevant. But exams, like I said, are not real life. And usually we will give you exactly the amount of information that's needed. So if you're going along with this question and you notice you haven't paid any attention to the fact that d of v equals 3, then that might be a good thing to look at. Okay, because in exam questions, unlike real life, we will normally not give you any irrelevant information. Everything we tell you normally will be relevant. Anything you haven't used, therefore, is potentially useful. Okay, so going on with this, that means let's do it the second way I did, perhaps. I think that's slightly clearer than the first way. Okay, so let's put it this way. Let's say the rank of t equals 3 minus the nullity of t, and that's going to be less than or equal to 2. But we know rank t is greater than or equal to 2. And so how can those two things be true simultaneously? Only one way, which is that rank of t equals 2. And then from the rank nullity equation, let's give that a label perhaps, equation star. So from star, we get nullity of t equals 1, and we've finished the question. Okay, so any questions about any of this? If I was writing too fast, please tell me and I'll show you the page again and you can take a screenshot.
Can I just make 2 comments on this?
Sure, please do, yeah.
First of all, I really enjoyed how you separated the thinking and scribbling and just putting stuff down from your answer. As I'm sure you've seen in exams, there's a lot of thinking that goes on. There's a lot of writing stuff down and kind of teasing out what the issue is. And not all the time does someone then present that thinking into a nice answer. So you made it really easy you made it really easy for the marker to come along and see, here's the answer, and you didn't make me have to trawl through all the scribbles to see that you actually understood the question.
Can I just butt in with a comment, just a comment there for the students. If it's a totally routine question, like say reduce this matrix to echelon form, then probably no scribbling should be necessary. You just write out the answer straight away. But for a question which is more, like I said earlier, more out of the box like this one, then I think you should do some scribbling first.
Yeah, and then as David has done, tell us which of those parts of put all that scribbling together in a nice little narrative for us, just to really drive home that you packaged it all your thoughts up neatly into a concise answer. And the second thing is I really like how David's written things like nullity of T is the dimension of the kernel. And this is the rank nullity theorem. Little gems like that are really useful. First of all, they're useful because you need that information, and it's nice to have it down on the paper so you can reason with it. But it's really useful to the marker who can then say, well, maybe if the answer is wrong, at least we can award partial marks because the student's demonstrated a good understanding of the topic and knows a lot of the stuff. So it's always a good idea to put stuff like that down.
Yeah. So it's a win-win situation. It's good for you, and it's good for us as well.
Awesome. All right. I'll go on with the next question. Again, if everything freezes up, I'll be back in just a minute. But let's hope this goes well. Hey. All right. Hey. Next question. We're given the cumulative density function of a continuous random variable x, and we're told what it is, and we're told that there's an alpha and beta involved. Okay, that's looking a bit big, and there's this thing called the cumulative density function, so we might want to think about that for a moment, but let's keep reading. Part 1, find the value of alpha and explain why beta is a quarter, and then calculate some probabilities, and then calculate an expected variable and a variance, expected value and a variance. These kinds of things are pretty normal things that you would expect to do with a probability, a random variable, but we're not really given all the tools you might want. Normally, when you're dealing with a continuous random variable, what you really truly want is the density function. For a discrete random variable, it tells you all the probabilities. For a continuous random variable, it tells you all the things you could possibly want to know, all the probabilities, and you can really work with that. But they gave you the cumulative density function. So it's a little bit different to what you might expect. So let's work with this, shall we? So this is question 2, part 2. Let's just remind ourselves what the cumulative density function actually says. The probability for the continuous random variable x, the probability that the value is less than or equal to k is equal to the integral, not the sum as in discrete random variables, but the integral from negative infinity to k of the, actually I might change that to an x just to be consistent, x of all the probabilities up to that point. So that's little f of t dt, which is equal to the cumulative density, capital X of x. So I'm gonna italic x for little x, capital X for random variable x, where little f is the probability, is the density function, and big F is the cumulative. So just to get all that stuff down there, we're given a question about a cumulative density function, but it's not necessarily the thing you want to be working with here. You really want to be working with this guy. Okay. And we're actually told what the cumulative density function is, so maybe we should write that down. So we can even include that piece of information here. It's going to be 0, where x is less than 0, less than or equal to. Beta x squared, where 0 is less than x is less than 2. And alpha for x greater than or equal to 2. And I'm even going to draw that. just because I'm just that way inclined. So let's go. And so that's 0, 1, 2. Theoretically, there's 0 values off here as well. Don't really care about those though. And what does our density function look like? Well, we know it's going to be equal to 0 all the way over here. It's always equal to 0 up there. It's equal to alpha when we get past 2. And it's going to look like beta x squared as we go up like this. So it's going to look like bit like x squared, bit like a parabola. It's going to look a bit like that. So that's our, this is our probability density function. Here are our x values, and this is the function f(x) of the x values. Okay. Let's start answering some questions. We're asked to find alpha, and we're asked to find beta. Now, the limit as x goes to infinity. As x gets really large, the probability that the random variable, whatever it represents, whatever it is, the probability that our random variable is less than some really large value will eventually be equal to 1. So let's put that 1 over there. Remember, this is the cumulative probability function, which is equal to, so I'll just put that in there, capital F x of little x, which is equal to, well, as x gets past 2, whenever x gets past 2, that's just going to be equal to alpha. Okay.
Daniel, could I just make a comment about the question? Because I just noticed, I don't think the question is actually quite written correctly, because this is, unless they were using different terminology in term 3 last year, we're calling this the cumulative distribution, not the cumulative density function.
Oh.
Yeah, so I think maybe they were using terminology differently last term, or maybe
it could be a typo.
It could just be a typo, yeah. So I think we should cross that out and make it cumulative distribution function.
Cumulative distribution.
Yeah, I think you're saying the right things, but just to clear up the terminology for the students.
Thank you. Yeah. I have the book here, but I won't pull it out right now.
No,
it probably does mean distribution.
Yeah, it does say density in the question, but I'm pretty sure that's definitely wrong the way we're using the terminology this term.
Yeah. It's probably got mixed up somewhere between the density function and the cumulative distribution. Okay. In any case, it means the probability that the random variable x is less than that value, and as that value gets larger, this thing has to go to 1 because probabilities have to add up to 1. So alpha is equal to 1. And maybe I'll just add that to my picture so I can reason with that a little bit better. And all your cumulative distribution functions will eventually tend to 1 as they get on towards positive infinity. Also, they're continuous. Since the it's continuous, then now you know that because it's a continuous random variable, so it can't have any jumps in it. So it has to be continuous. I can't spell continuous. So the limit as x approaches 2 from below of f of x, capital F of x, x must be equal to fx of 2, which is just going to be equal to 1. But on this side, that's equal to, well, b, the limit x approaches 2 from below b x squared. Hence, this one here is just going to be equal to b times 4 is equal to 1, and b is equal to 1/4. Now, did you need to go through all that stuff? Well, maybe not for alpha, but yes for beta. So the question asks you to find the value of alpha. Okay, you could just say alpha is 1. Maybe, and if you said alpha was 1, then no one really needed to look any deeper than that. But you did have to explain why beta was 1/4. The question explicitly asked you to explain it. So there needed to be some reasons there. You already knew beta equals 1/4, and you get no marks for saying that beta is equal to 1/4. You had to justify somehow why beta was equal to 1/4. Okay, next part. Calculate P. Oh, so part B. Part B asks you to calculate P, the probability that 1 is less than or equal to X is less than or equal to 2. And the good news is, oh, you can't see what I'm writing. The good news is that you didn't really need to know anything, or you didn't need to know too much about probability, the density function to actually do this, because the cumulative distribution will tell you what that is. This is just equal to the probability that X is less than or equal to 2 minus the probability that X is less than or equal to 1. So on our graph, it's really asking you what is this shaded region here? What is the probability that X is between 1 and 2? And that you're going to get that by just taking this value minus this value. So not the shaded region, but what is that value minus that value is going to give you this thing, because this is just capital F X of 2, and this is capital F X of 1. Yeah, not the shaded region. Sorry, I'm thinking of the density function again. But just that value this value minus this value, which we can just plug that into our little formula for what capital F is. It's going to be equal to alpha, which we just discovered was 1, and capital F applied to 1, that's going to be 1/4 times 1 squared, which is 3/4. 3/4. Now calculate the expected value of X. This is part C, the expected value of X. Now this is the part where you might wish you had the density function around. The expected value of X is the integral from -infinity to infinity of all the values that your random variable can take, times by the probability that X is equal to that value, little x. dx. Now we wish we had those little probability functions around. This one here, or maybe I won't write it quite like that. Maybe I'll write it like this. X times f of x dx, where so for this question, we kind of do want the density function, but fortunately, we almost have it. We almost have it. So I'll remind you that. Let's see now. If a little x is less than or equal to 0, then the density function is equal to 0. Now we can see that from our probability, our cumulative density. The probabilities up to the point here, the cumulative probability that x is less than 0, capital X is less than 0, is always 0. So the probability of the density function is always going to be 0 at that point. And similarly, after 2, the probability density function is always going to be 0, because you've got all your probabilities. There's no way your variable x is going to be bigger than 2 or less than 0. So if x is less than 0, then you know that. And if x is greater than or equal to 2, then f of x is also equal to 0. So we really only want to know what happens to this function when x is between 0 and 2. And so if x, maybe, and if 0 is less than x is less than 2, then this thing being our definition of the density function is equal to 1/4 x squared. This is the kind of thing I can bust the fundamental theorem of calculus on, because I want to know about that. I can differentiate both sides, dx. Maybe I'll replace that with, I could replace that with a 0 actually, that might be more pleasant for my fundamental theorem, is equal to dx of 1/4 x squared is equal to the derivative of this is going to be half x. And this one over here is just going to be the density function. Hooray, I found the density function. So the expected value of x, the thing I wanted to calculate, is going to be this thing, which is going to be, well, I'll break that into 3 integrals. That's going to be negative infinity to 0 of x times f of x, plus the integral from 0 to 2 x times f of x dx, plus the integral from 2 to infinity x times f of x. But this one is going to be 0 because the function has no density in that area. So this one's going to just go away. This one's just going to go away. And this one is going to be replaced with something I quite like, which is the integral from 0 to 2 of x times f of x. And on this range, f of x is just that. So it's going to be x squared over 2 dx, which is x cubed over 6 from 0 to 2, which is 8 over 6, which is 4 over 3. So my expected value is 4 over 3. Part D says we're given the expected value of x squared is equal to 2. Find the variance of x. Now, there's 2 things about this that I want to say. The first one is there's a nice formula for the variance of x involves the expected value of x to x squared, and it's worth remembering where it comes from. The variance of x is equal to in your brains, what I want you to, a useful way of understanding the variance of x is as the expected square distance of x from the mean. So it's really a measure of how far away your random variable is from the center, from its center of mass. So is it a really fast spread, or are things really clumped up around the average? Your variance is a kind of numerical measure of that. And you can write it as the expected value of the difference between x and its expected value, all squared. So the difference between x and the expected value of x, you square it to make it a square distance, and then you take the expected value of that, so you get a nice numerical answer instead of this thing, which is a random variable. You want just a number, so you take the expected value. This is, I mean, you can just remember this, or you can expand this out. The expansion would be, the expansion is not too bad. It's just a quadratic. So this is minus 2x ex plus ex squared. And that's going to be, now use the fact that expectation is actually a linear operator. So you've seen a linear transformation. You've seen linear transformations before. You know what they do. This is going to be the expected value of x squared minus 2 times the e of x times the expected value of that x plus e of x all squared. And here you've got e of x squared. You've got minus 2 of them. Plus 1 means there's minus 1 left. And here you have an alternative, but in this case, much more useful formula for the expectation. So this is a nice definition. I like this one because it makes sense to my heart, but I like this one because it makes sense to my calculator. Both of them are quite useful. Sorry, I'm just looking at the chat. Come back here, chat. Should the last term be expected value of the expected value of x? The last term be expectation of expected. Yes, it should, but that's the same thing. So I might remind you that expected value of a constant, say constant, is the constant. So your expected value, so e of x is just e of x. And you are right to say that. I've just snuck that in because yeah, I've just snuck that in. Cool, thank you. But thank you for paying attention. Thank you very much. Now I've got all the bits that I needed. I know that the expected value of x squared is 2 because that was given to me, and I know this is just the square of the value I had previously. That's just 4/3 all squared, which is 2 minus 16, 16 over 9, which is 2 over 18. So the variance here is 2 over 18. I don't know if there's a way to, yeah, I wouldn't use that formula. I definitely use that one, and it's kind of suggested to you by the fact that they gave you this. The only other thing I wanted to mention about this question is they gave you that the expected value of x squared was equal to 2. And that piece of information is quite, you could have derived that, but because they gave it to you, you can check that your answer is sensible up until this point. So to just verify that the expected value of x squared. Now the expected value of x squared, so verify working. Expected value of x squared will be the integral from -infinity to infinity of x times the density function f of x. Sorry, x squared times the density function of that thing, dx. And so instead of x, like we had previously, you just have the function of x, which is the square function, and we just put that there. So whatever. Yeah, so we're just squaring it because we're taking the expected value of the square function. And this, as we did before, is just going to be 0 to 2 of x squared times x onto the x, because the density is 0 everywhere else. And that's going to be the integral x cubed on 2, 0 to 2, which is x to the 4 on I have to divide by the new power, so that's 16. No, 8. 0 to 2, which is 2 to the 4 on 2 to the 3, which is just 2. So it's just nice to go, because they don't give you the answers in the exam. You might really want to know, oh, geez, was that, am I on the right track here? Was this truly the density function? What am I doing? You invest a lot of time and effort into this question, and then they throw something to you like the expected value of x squared is 2, and you can use that. A, you can use that to answer the question you're given, but you can B, use that to just verify that, hey, the things you've done so far are actually on track. This makes a lot of sense because with your calculations, you also know that the expected value of x squared should be 2. David.
Okay, so yeah, if there's no more questions there for Daniel, let's go on to part 3 of question 2, which I've just got right here. Just coming up in a second. Okay, so here we go. Here's the question. Back to linear algebra. So let A be an invertible n-by-n matrix with transpose A transpose. They're just telling you that in case you've forgotten what the notation A is. Let V be an eigenvector corresponding to the eigenvalue lambda. Show lambda is an eigenvalue of A transpose, and B, let's come back to, I'll read through B later. Okay, so let's have a think about this one. So lambda is an eigenvalue of A. And here's something that, here's an approach you might care to use. Don't necessarily use this all the time, but it might work. What we're aiming to prove is that lambda is an eigenvalue of A transpose. So I'm going to write what we know at the top. I'm going to write what our aim is at the bottom, and then leave a gap to be filled in here. Okay, so can anybody suggest the fact that, I'm just going to go back to my chat so I can see the. Can anybody say if lambda is an eigenvalue of A, and if we want to say that without any reference to eigenvector, what does that mean? How do we actually find the eigenvalues? What's the equation? Can anybody remind us? What's the equation for an eigenvalue? Determinant, yeah. Can anybody tell us specifically the determinant of something equals something? That's the right idea. I'm sure you got the idea, Teresa, but can anybody give us the full details? So A, yeah, and equals, right-hand side equals 0. Okay. Okay, yeah. Okay, great, yeah. So M, yeah, first the A instead of M, but that's the right equation, yeah. Okay, now, again, let's try and let me not just tell you the answer, but see if we can think about it. And if you look at this, this is what we know. This is what we want to know about. Could anybody suggest what is there in this desired conclusion that does not seem to have anything yet to do with this? What's there in here that we're not talking about yet? Just a one word or maybe even one letter answer would do for that. Again, it's not as straightforward. The transpose, yeah. Again, it's not a straightforward question, so I want to try and show people how you can think about this, not just what the answer is. So we've got to get the transpose in there. Now, does anybody? I'm going to do a scratch pad on my scratch pad here. We're talking about determinants. We're talking about transposes. And if we think about, let's never mind what that matrix is. But for now, determinant of M. Can anybody remember anything, how we can get a transpose in there? What's an important relation involving determinant and transpose? Okay, one thing that you should know about determinants is the determinant of a matrix is not inverse, but is the same as the determinant of the transpose. Okay, determinant of M is always the same as the determinant of M transpose. And if you remember, for your basic ways of evaluating determinants, you can evaluate them by going across a column or you can evaluate them by going across a row, or you can evaluate them by going down a column. And this is related to the fact that the determinant of a matrix is the same as the determinant of the transpose of that matrix. This is for square matrices, of course, because otherwise determinants don't make sense. So we could say here, determinant of A minus lambda I transpose, maybe I should put more brackets there, also equals 0. It equals the same thing, equals 0 therefore. And now you need to know some of your algebra about determinants. Could anybody rewrite that bit, that this in brackets transpose? How could I write that? Remember that transposes respect addition and subtraction. In fact, taking the transpose is a linear operation. So I can just say that's A transpose minus scalar times I transpose. Okay, so I'm saying this determinant equals 0 because that's what an eigenvalue means. And then I have to come up, this is the hard part, I think. To me, this is the hard part, because you have to come up with an idea here, because obviously there's lots of things you could do with that. How do you know that taking the transpose is the right thing to do? Well, the answer to that really is you don't know. This is something you've got to think up. And a guide to it is that what you're aiming for includes the transpose, and what you have at this stage doesn't. So somehow or other, we've got to get a transpose into our problem. But how do you know it works? Well, as I said, the short answer is you don't. That's just something that's worth trying. And then if you get that part, I think it's not so hard to go from here, because how could I simplify this further? What's I transpose? Remember what I is, and what's I transpose? One letter answer will do for this. It's just I, yeah, right? Because remember, I is just this matrix here. It doesn't even say how big is it, does it? It's an n by n, but everything that I haven't written down here is 0. And if you transpose that, swap the rows and the columns, you get exactly the same thing back again. So I transpose equals I. And now what is this equation here telling us? That's exactly what we started with. Lambda is an eigenvalue of A. Exactly the same, except now we've got A transpose instead of A. So this is telling us lambda is an eigenvalue of A transpose, and that's exactly what we wanted. Okay, any questions on this one? In this case, the rough working worked out so neatly that we could possibly even present that for an answer. We might want to put in some other reasons. I might say something like this. Suppose lambda is, I won't write this down, I'll just say it. Suppose lambda is an eigenvalue of A, then the determinant of A minus lambda I equals 0. Since the determinant of a matrix equals the determinant of its transpose, we have determinant of A minus lambda I transpose equals 0. Then I might say something like, by properties of transposes, determinant of A transpose minus lambda I transpose equals 0. And then I would say, but the transpose of I is equal to I, therefore determinant of A transpose minus lambda I equals 0, and this means lambda is an eigenvalue of A transpose. Any questions so far? Okay, so let's have a look at the second part of the question. I think we're running a little short of time, so I'm just moving a little faster than I have been before, but do feel free to stop me if there's anything that's not clear. So second part, show you cannot conclude that V is an eigenvector of A transpose. I'm going to rewrite that question, because here's an answer. Show that you cannot conclude that V is an eigenvector of A transpose. I can't conclude it because I don't know anything about eigenvectors. Well, I don't think that's the answer we're looking for. So what they mean is find an example where V is an eigenvector of A, but not an eigenvector of A transpose. Let's rewrite the question that way. So find an example, in other words, find a matrix A and a vector V. Find an example where V is an eigenvector of A, but not of A transpose. So yeah, I think that's a much better way of writing the question. The way they've written it encourages silly answers like what I just said. Okay, and well, basically they've given you a hint. So what do you think? So you have to find a matrix A, you have to find a matrix, a vector V, you have to confirm that V is an eigenvector of A, and you have to confirm that V is not an eigenvector of A transpose. What could we take as a guess for A and V? Well, I think the hint here is pretty obvious. So let's just try seeing if we can work that out. So for B, I'll say take A equals the matrix 3, 2 in the first column, 1, 2 in the second column, and V is the vector 1, 1, just straight off what's given there. Then I can say A times V is equal to, and we've got that in the maple, it's 4, 4, as long as you understand that the maple notation A dot V means a matrix times a vector, as long as you understand it. So that's reason from maple. Okay, and now what's our basic eigenvalue equation? How do I know that V is an eigenvector? What's the particular point of this? I could write this is, any suggestions? You could write a number and a letter for that if you like. Yeah, AV equals lambda V, with lambda in this case. And so what's the lambda in this case? It's going to be 4, because that's clearly 4 times this vector here. So AV equals 4V. Okay, and so V is an eigenvector of A. Okay, does anybody remember, to be completely precise about the definition of eigenvector, it's what Dominic just said, AV equals lambda V, and one other thing. One other fairly minor looking condition. Okay, remember that by definition, an eigenvector is not 0. So let's just put that in as a comment. So and V is not equal to 0, which is obviously true because this is V. It's clearly not 0. Okay, I don't think we'd take any marks off if you left that out. So V is an eigenvector of A. However, we have to show that V is not an eigenvector of A transpose. So let's work it out. A transpose V is 3, 1 first column, 2, 2 second column, times 1, 1. Do the multiplication, you get 5, 3. And now that's clearly not a scalar times 1, 1. Therefore, 1, 1 is not an eigenvector of A transpose. And I'll just write down exactly what I said. This is not a scalar times 1, 1. So 1, 1 is not an eigenvector of A transpose. So just to make sure everybody's clear on what's the point of this question, the point is that suppose you've got a matrix A and you've got an eigenvalue lambda for A with an eigenvector V, then you can say that lambda will also be definitely an eigenvalue of A transpose, but V does not have to be an eigenvector of A transpose. So again, to put it perhaps another way again, you can say that A and A transpose will always have the same eigenvalues, but they may not have the same eigenvectors. That's the point of this question. Right, any questions on these things? Just one, let me just ask one more thing. Can anybody notice anything? Here's the question again. I said before that normally in exam questions, we won't give you any unnecessary information. But I think we actually have done so in this question. What's in the question that we didn't actually ever refer to at all in our answers? Can anybody see? Have a look at the question. What did we not use at all? Just read through the question. That's invertible. Yeah, Philaretus. Yeah, thank you. Yeah. So they could have left that out, and I suspect maybe somebody made a slight slip there and left it in. But I think they could have left that out, and the answer would have been exactly the same. Okay. Any questions on that? Okay, Daniel, you ready to go on with the next part?
I'll just attempt to share my screen. It's been really good for me today. It hasn't died at all, but here I go one more time. All right. Okay, so the next question, thank you. The next question is this one. Suppose that 45% of the voting population are Labour voters. And maybe I'll remind you that this is term 3, 2019. So it's recent. The exam was written about the same time as the election. A sample of 200 people is selected at random from the population. Use the normal approximation to the binomial distribution, including the continuity correction, to estimate the probability that more than half the sample voted Labour. Interesting, and at the time very contemporary. So will we have a COVID-19 question? The exam would have been written before that got real serious, but maybe I'll maybe definitely term 2. You can expect lots of COVID-19 questions in term 2. All right. Suppose okay. What's going on here? Question IB. So what we're going to do here is take a binomial random variable and formulate a question using our binomial random variable, and then answer that question with the continuous, with the normal approximation to it. That's right. Okay. So let x be equal to number of labor So x is the number of labor voters in the sample of 200. Then we would say x has the binomial distribution. The probability of success in this term, in this case being defined as voting labor, is 45 out of 100, and there are 200 samples. We are asked, what is the probability that x is bigger than or equal to, bigger than a half? Find the probability that, is more than half the sample vote labor. So the probability that x is bigger than or equal to 101. So that's the question we're being asked here. You've got this percentage of people voting labor in a sample of 200. What is the probability that more than half of them vote labor? Which is possible, and in fact that may have occurred during the samples that the exit polls and such, or the pre-polling that occurred before last year's election, which is, I suspect, again, why this question was created. Let me draw a picture, because I like pictures. Can't survive without pictures. What's going on here? So the expected number of people who are going to vote Labour in this thing, in 200 people, is, maybe I'll just put a few things down here, is going to be 90. So you would expect if 45 out of 100 are going to vote for Labour, and you have 200 people, then 90 are going to be 90 is what you would expect. So here's a, and this time we are working with the density function, so that's nice. So here's the 90, and 90 is going to be the biggest value here. So this is the 90 value, and the area of this rectangle represents how many people voted, or the probability that 90 people vote for Labour. And then you've got 91, 92, ... And then down here somewhere you'll have 99, 100, 101, 102, and so on. And there's going to be little rectangles going on everywhere. I'm just going to draw them in because it makes me feel good. Ta-da. And maybe the rectangles getting shorter and shorter at each point. Now, we want to know what is the area of this rectangle, 101. So that would be the case where exactly 101 out of the sample vote Labour, or 102, where exactly 102 people vote Labour, or 103, or 104, and even up to the case where the sample is taken from a Labour conference and all 200 people who are sampled vote Labour, which is very unlikely, but could happen in theory. So, what is this area? You might know by definition that the probability that x is greater than or equal to 100. Well, you could say that's equal to the sum from k equals 100, 101, and k equals 101 to 200 of the probabilities that x is individually equal to k, but this is going to be a somewhat beastly sum with 99 terms in it. You don't want to 200 terms in it. You don't want to go summing up something like that. Instead, what we do is we take the normal distribution. I would say a normal approximation to it. Now, the normal approximation is a continuous version of this one here. And its density function goes through all the centers of each of these blocks, all the way down. So if this is our random variable x, we need two things. We need two things, and coming, dot, 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 all the way up there as well, being a nice kind of its density function approximates the binomial density function, dot, dot, dot. Like that. So we really want to know what is the continuous version of this random variable, and then use that to estimate this area down here. So we need two things. We need the expected value of x. In general, that's going to be the probability of success times by number of samples, which, as we saw before, is just going to be 90, and the variance of x. Please do calculate this variance using your definition. You should, I advise you memorize the definition times for the variance for the expected value, or the variance for the binomial distribution, just because it comes up so often, which is equal to, well, that's just 90 times 55 over 100, which is you could probably, no, Clever, you could do that now. You have the power. It's just much faster. It's just you don't want to be spending your time doing that. So that's definitely one of the things I'd put down for memorization. You don't want to be doing that in this exam because it's just going to take you too much time. So that's going to be 9 times 11 on 2, which is 99 on 2, which is 4.5. Okay, so we got the expected value, we got the variance, and you got them quick. You don't want to spend half a page doing that. Then x, the probability that x is greater than or equal to 49.5. Thank you, 49.5. The probability that x is greater than or equal to 101 is approximately equal to the probability that y is greater than or equal to. Now I'm going to do something fancy in a moment. Well, I'm going to do two things, but let me break it down for you in a moment. So let y be a continuous random variable with y with having the normal distribution, expected value 90, and variance 49.5. So it's a bit squished in there. Then this is the density function for y. So here is my probability density function. The red one here is the probability density function for y. And this discrete one, these blocks, are the probability density function, the one for my discrete random variable. So you can see that if I construct my random variable y with this very particular distribution, normally distributed with the same expected value and same variance as x, then they kind of hug each other real tight. Now, I want to try and use y to estimate this area. And you might say, well, the probability that this is going to be equal to the probability that that. But if we look real close here, if I start my integration from 101 I've missed half of this block. And so a slightly better approximation will be to wind that back a little bit by half the block and integrate from here onwards, and thereby capture, make a better approximation to the sum of those blocks. So instead of this one, I'm going to wind it back to that. And this is what's known as the in the question as the continuity correction, that winding back. They've been quite explicit that you need to do that. Of course, if you don't do that, then you'll be slightly off, and it's an approximation anyway, so you're still mostly correct. In this question, they've been very clear that you have to do that. You have to wind it back by that little bit. Okay. So we've got this normally distributed random variable, but it's not normally distributed in the sense that, well, you've got that whole big table on, which is in the back of your exam. It's not normally distributed in this sense because this is the normal distribution with n0, expected value 0, variance 1. So we need to convert out this thing into something that is normally distributed with expected value 0 and variance 1. So that's going to be equal to the probability that y minus the expected value, which was, again, 90, is greater than or equal to 100.5 minus 90. Okay. Now what this has done is taken my random variable y and recentered it so its expected value is actually 0, just shifted it over. Shifted the whole thing over. But it still doesn't have the right shape, it still doesn't have the right variance. To get that, you need to divide by the standard deviation. So this will be y minus 90 divided by the square root of 49.5, which will be bigger than or equal to, this is going to be 10.5 over square root 49.5, which is equal to, I'm going to write that as probability that z is greater than or equal to, and I need my calculator for the next bit. Can't hit the calculator. $10.5 divided by square root, go away. 10.5 divided by square root 49.5 equals 1.49. Now, the reason I've done this, the reason I subtracted the or recentered and then renormalized my discrete random variable is that I can say let y minus 90 on the square root of the variance equals z is a normally distributed random variable centered at 0 with variance 1. This, which makes this thing the kind of stuff that I can look up on my table. So I grab my table. I want to know. Oh, my table tells me probability that z is less than something. So I say that's 1 minus the probability that little z, okay, z is less than or equal to, maybe not equal to 1.49. 1.49. That thing. So that's 1 minus 0.9319, which is, what's it going to be? 1860. Hooray! Oh, sorry, you can't see that. So, which is about 7%. So even if only 45% of the population will vote for the Labour Party, there's a 7% chance sampling will tell you otherwise, which is a lesson that a lot of pollsters learned in 2019. David, over to you. Hello.
Okay, hi, I'm back here. Dominic, was that a question, or sorry, I wasn't?
Oh no, the 49.5 is correct.
Oh, that was,
I wrote 44.5 and she
oh, right,
corrected me.
right. Okay, sorry, I lost. Was not paying attention there.
Yep.
Okay, thanks. I'll share my screen back again for the last part of this question. Okay, and here we go. So we've got the question here. Let T be a linear map from R9 to R7. T of X equals a matrix times X, where A is shown below. Using the Maple code, answer the following questions. Write down a basis for the image T and a basis for the kernel T. It's, in a way, it's perhaps slightly unfortunate this is the last question, because this is really a very standard one, and I hope everybody should be able to do it without too much trouble. So let me just, I couldn't be bothered copying down the matrices, so here we go. Here's the exam. So that's your matrix A. And the first question is find or write down a basis for image U. Write down is nearly always a hint. It should mean that that question is so easy that you should just be able to see it and know how to do it and write down the answer. So remember, the procedure for that is you'll take A, you'll reduce to row echelon form. Now, obviously, we would not want to do that in this case, but that's why they've given it to us by Maple. This is the reduced row echelon form of A. And then if you remember the technique for this, to find a basis for the image, I should mention perhaps it says image of T. If T of X equals AX, that's the same thing as the image of A. Okay, so the technique is to reduce A, echelon form, that's what we've got right here. And then you look for the leading columns, and those are columns 1, 2, 3, 4, 5, 6, not 7, 8. So 1, 2, 3, 4, 5, 6, 8. And then a basis for the image would be the corresponding columns back in the original matrix. Okay, so let's just write that down again. Okay, I'll say for the say part A, the basis vectors for image of A, perhaps we'll put in a comment, or image of T. If T of X equals AX, it's the same thing. Are those, and let's emphasize this because this is one thing that people sometimes get wrong in this, are those original columns, not the row reduced columns, but the original which correspond to leading columns in an echelon form for A. And then we can say from output, these are columns 1, 2, 3, 4, 5, 6, 8. And let's just, as I said, this up here, doing the columns from the echelon form instead of the original is a very common mistake. So let's make it clear it's of A. Okay, so any questions about that? Okay, so I hope that's a pretty standard question and people can just write this down. I don't think we would expect you to write out the whole columns. Just something like this I think is very clear, and so let's just put it that way. I'll just mention, I'm sure what I've just said is what we were intending you to do, but could anybody find an alternative basis for this? Remember, the image is going to be the set of all possible T of V values or T of X values. So it's going to be in R7. We've found a basis here. So E7, yeah, I'm not sure, not exactly E7, but I think you're probably saying the right thing. Namely, it's the standard basis vectors. Yeah, so alternatively, you could say rank of the image, rank of A, yeah, E1 to E7, yeah, exactly. Good answer. We can say rank A is 7. From this, there are 7 vectors here, so the dimension is 7. Rank A is 7, and the so that is dimension of image of A is equal to 7. but image of A is a subspace of R7. Okay, and now if you have a 7-dimensional subspace of a 7-dimensional space, it must be the whole thing. So I could say image of A is equal to R7, in fact, and a basis is E1 up to E7. However, just a comment, I'm sure that's not what we're intending. I'm sure the first solution is the one that we were expecting you to do. This one gives you a simpler basis, but it does require a bit more work. So I think the first one is what you would probably go with. Any questions on this one? I hope that is a pretty easy one because it's a very standard problem. Given a matrix, find a basis for the image. You reduce to row echelon form, you identify leading columns, you look at the corresponding columns not in the echelon form, but back in the original matrix. Any questions on that one? Okay, so then let's do part B. And that also, there's a bit more work to do here. So we want to find a basis for the kernel T. And once again, if T of X is AX, then kernel of A, kernel of T is the same thing. Okay, so that is, well, remember we've done this before. I think always worthwhile thinking about the definitions. And we have done the definition of the kernel before. What it means is we have to solve AX equals 0. Okay, and now let's go back to, I'm going to see if I can get these two things up here simultaneously. So let me just resize things a minute. Okay, so I've now lost my chat, so if there's any comments, I'll have to take a little while before I reply to them. Okay, so something like this. So how would you do that? You would take the reduced echelon form. You would write, if you want to, 0 on the right-hand side. I wouldn't even bother writing it because that's really easy to remember that the right-hand side is 0. And then let's just look at the equations. So we get the following. I hope that's big enough for people to see, but I do need both screens simultaneously, both windows simultaneously. Now have a look at the echelon form. The first thing that you should see is that column 9 here, there are 9 columns. Column 9 is a non-leading column. Therefore, x9 is going to be a parameter. Let's call it lambda. Then if you look at the rows from the bottom up and reinterpret them as equations, the bottom row says x8 equals 0. So that's easy. If you then look at the next column backwards, column 7 is non-leading. And therefore, x7 also has to be a parameter. Okay, let me know if there are any questions, but I'm going to do this fairly quickly because I hope it is pretty familiar. Then if you look at the second last row, that's saying x6 equals 0. So this is all really easy. And the previous row says x5 equals 0. And the previous row, well, then they're starting to make it a little bit harder for you, but not very much, because that's saying x4 plus x5, 6, 7, 8 plus a half x9 equals 0, and therefore x4 is going to be minus a half x9, and I'm not going to write x9 here, I'm going to write lambda because that's what it is. And then similarly we keep on going. The third row tells you x3, and they've made it slightly harder again. It's going to be plus x7 plus a half x9 equals 0, and therefore x3 is going to be, so it's going to be minus x7, and again I won't write down x7, I'll write down mu because that's what it is, and minus a half x9, and x9 is lambda, so we've got that there. Okay, and then row 2, they've gone back to doing something easy for you. It says x2 equals 0, and row 1 says x1 minus 2x7 equals 0, and therefore x1 is equal to 2x7, in other words 2 mu. Okay, and so hence the kernel of A is the set of all x such that AX equals 0, and we can just write that down because we've solved it. It's x1, and I'm just copying from my previous page. You can't see it, but I'm just copying it down. Excuse me. So x1 was 2 mu, x2 was 0, x3 was minus mu, minus a half lambda. X4 was minus a half lambda. Fair bit of writing, but hopefully not too much thinking. Then x5 was 0, x6 was 0, x7 was mu, x8 was 0. Excuse me, too much talking. X9 was lambda. Such that mu and lambda are real numbers. And I can write it this way. Well, let's see, since there's so much writing, let's see if I can skip a bit of working, because this is very much like we did in the very first problem I did today. We want to write that as the span of something. Let me do, hang on, I'll just see if I can see that comment. Excuse me a moment. I'll just have to get rid of this window here. Oh, was there a comment there? Nope, can't see it. Oh, recordings, yeah.
Recordings, yeah.
Yeah, let's come back to that later, please. Let's just finish the maths and any other comments, please, later. Yeah, so remember what we do. I'll do the intermediate step just verbally. I would say that is mu times 2, 0, minus 1, 0, 0, 0, 1, 0, 0. And plus lambda times 0, 0, minus half, 0, 0, 0, 0, 1. And so it's the span of those two vectors. Once again, the mu coefficients were 2, 0, minus 1, 0, 0, 0, 1, 0, 0. Just check I should have 9 numbers there. That's correct. They're not very well spaced, but near enough. And the lambda coefficients were 0, 0, minus a half, 0, 0, 0, 0, 1. Okay? And so it is now, again, it's really exactly the same as in the first problem that I did for you today. Namely, this shows you that these two vectors form a spanning set for kernel of A or kernel of T, whichever. They actually asked kernel of T. So let me put at the top, perhaps kernel of T equals this. Same thing. These two vectors form a spanning set. It's, I think, pretty easy to see that they are not scalar multiples of each other and therefore linearly independent. Therefore, they form a basis. Okay, and just to avoid having to do too much writing, avoid having to write them down again, let's say the two vectors just shown span kernel of T. They are independent because they are not multiples of each other. It's actually fairly unusual in an exam for them to give you basically the same question twice, but that's pretty much what they've done here. So they form a basis for kernel of T. Once again, remember definition, a basis is a spanning set which is also linearly independent. Okay, so any questions on any of these things? Or Daniel, any other things that we should mention? Or I guess then we're down to...
Go on, sorry.
Sorry, I was just going to say, if there's no other questions, then perhaps the administrative questions like where are the recordings and so on?
Yeah, I think the recordings are just using this same link, aren't they? I've not actually watched a recording.
I think, hang on, let me just see if I can find it. I might be able to find it here, seeing that people are able to see my screen.
Okay.
So you go back to this session here, and I'll get rid of that side panel. And this menu up here, you have recordings. And I don't know if it's there immediately, but well, I won't look through it because there's heaps of things there. But anyway, that's how you do it. You go through this menu here. Sessions are what we're doing now. Recordings are where you find the recording. So yeah, anything else on that? Or any other questions about the mathematics, or I guess just general questions about anything? What's the weather like? It's stopped raining, but it's still cloudy.
It's very cold.
Yeah. So yeah. So if there's let me just remind you. It's still when's the exam? End of next week, I think, isn't it? So please remember, there's still heaps and heaps of help available. There's staff consultations every morning, 10 till 12. Every afternoon, 2 till 4, and occasional evenings, 8 till 10 p.m. That's through the usual staff consultation part on Blackboard. There's the Maths Drop-In Centre. Again, I'm not quite sure exactly what the times are, but it's available a lot of the time. And you can always email people and ask questions.
And the forums as well. I believe the forums are still operating
forums,
as a
yeah.
place you can
I think
questions
so.
answered.
Yeah, I believe that's. Yeah. Thanks for coming, Philoretus. Good to see you here.
Yeah, thanks everybody, and good luck with your studies.
Okay. I'll just turn off the recording.